All right, folks, welcome back to video 2 of section 10.12 of AP Calculus BC, the Lagrange Error Bound. And we're going to continue with some examples related to Lagrange Error Bound in this lesson. Let's start here with example 2. The approximation sine of x is approximately x minus x cubed over 6 is used when x is small. Find the Lagrange error bound when the absolute value of x is less than 1. Now, these sine functions and cosine functions are a little bit tricky when we talk about Lagrange error bound because technically this polynomial is the third degree Maclaurin polynomial. It's also the fourth degree Taylor polynomial, or Maclaurin polynomial, however we want to describe it. It's both a Taylor and a Maclaurin. Because the x to the fourth term is, 0x to the fourth, the next term that shows up in this polynomial would be x to the fifth. So this is both considered the third degree and the fourth degree polynomial. Now, something you need to realize in this context is when you look at the Lagrange error bound, the fourth degree Lagrange error bound is going to be smaller than the third degree Lagrange error bound. And so we are always going to opt to get the tighter window of error here for ourselves. And it's most appropriate for us to, instead of finding the third degree error bound here, for us to find the fourth degree error bound here. So that's what we're going to look for. We're going to say that the error here is less than or equal to the fourth order remainder, which is the max of the fifth derivative of x times the max of absolute value of x minus a to the fifth all over 5 factorial. And so now we need to set that up. Now, in order to do this, we need the fifth derivative of the function. So we start with our function being sine of x. The first derivative is cosine of x. And for those of you who know about the cyclic nature of sine and cosine derivatives, you can jump right to the fact that the fifth derivative is cosine of x. And so if we think about this, on the interval where x is negative 1 to 1, I'm looking for the maximum value of cosine of x. That maximum value is going to be 1, because cosine of 0 is equal to 1. And in general, when we have sine of x or cosine of x, a lot of the times we won't even think about it. We'll just say, the maximum that can be is 1. And we'll use that in computation, even if we've got a slightly better approximation that we can come up with. But in this case, it actually is, because the cosine of 0, which is in this interval, is 1. And so the maximum value is going to be 1. So our error becomes the maximum value of this derivative is 1. The maximum value of absolute value of x minus a, this series is centered at 0. We're looking at the interval from negative 1 to 1. And therefore the maximum width of that interval is 1. Can raise that to the fifth. We've got all of that over 5 factorial. And so our error here is going to end up being less than or equal to 1 over 120. Or if we write it as a decimal, if you do 1 over 120, we want to round this up. So we're going to route that as 0.00834 for our error, if we want to write it as a decimal. All right. On to the next page, example 3. For approximately what values of x can you replace cosine of x by 1 minus x squared over 2 with error magnitude no greater than 5 times 10 to the negative fourth? Again, this looks like the second degree approximation, but since there are missing terms, this is both the second degree and the third degree. So we're finding a third degree remainder. Now, what this problem says is we want the error magnitude to be no greater than 5 times 10 to the negative fourth. All right, so our error needs to be smaller than 5 times 10 to the negative fourth, which is Did I go 1, 2, 3, 4? Yeah, needed to count my zeros there. 5 times 10 to the negative fourth. So we want our error to be less than or equal to that value. All right. So we want the third order remainder to be smaller than this. So we're looking to set the third order remainder, and we want it to be less than or equal to 0.005. And now we're going to find an interval instead of, an error bound. So let's go ahead and set this up. The third order polynomial is going to be the max of the fourth derivative of x times the maximum of x minus a to the fourth all over 4 factorial. We want that to be less than or equal to 0.005. I think I said one too few zeros there. Now the fourth derivative of our original function, since our original function is cosine, the fourth derivative of our original function is also cosine. And the maximum value of that is going to be equal to 1, which enables us to set up this relationship that the absolute value of x minus a to the fourth power over 4 factorial has to be less than or equal to 0.0005. Now, our series is centered at a equals 0, because the cosine function is centered. This is a Maclaurin series. It's centered at a equals 0. So I'm actually going to go back here and I'm going to change this from x minus a to the fourth and change it over to just x to the fourth because a is 0. And now I can solve this inequality for x. I've got that the absolute value of x is less than or equal to, and I'm going to take 4 factorial times 0.0005, which is going to be 0.0012, right? 24 times this. Oh, no, I've got one too many zeros in there, right? Sorry, my brain's firing a little short here. So we've got 0.0005 times 24. I'm on the struggle bus right now. 0.012. And then we take the fourth root of that value. So we're going to raise that to the 1/4 power. And it's going to give me 0.330975, etc., etc. Now, since we're writing this as an interval, normally we round the error up. With intervals, we're going to round them in towards the center because the error is going to be smaller than this, guaranteed to be smaller than this at 0.3309, but it's not guaranteed to be smaller than this at 0.3310. So I'm going to round towards the center of the interval, and so our interval here is going to be from negative 0.3309 to positive 0.3309, and that's the interval on which the error has a magnitude no greater than 5 times 10 to the negative fourth. All right, keep plugging away. For approximately what values of x can you replace e to the x by 1 plus x squared over 2 with error no greater than 5 times 10 to the negative fourth? So here we want, this is the third order error. We want the third order error to be less than or equal to 0.0005. Again, this is going to be centered at 0. So we set this up as the maximum value of the fourth derivative of x times absolute value of x to the fourth all over 4 factorial has to be less than or equal to 0.0005. And the fourth derivative of our function is e to the x. And so the maximum value of that is going to happen at the right endpoint of this interval. Whatever the right endpoint is, if you think about it, e to the x continues to grow as we move from left to right. So at the right endpoint of this, that's where the maximum value is going to be. Since we're looking for an interval, that's what we want to find. So the maximum value is going to be whatever e to the x is at the right endpoint. And so this is 24. And so I want to solve this equation. E to the x times, and the absolute value of x to the fourth is just x to the fourth, has to be less than or equal to 0.012. So I'm going to go ahead and solve this equation in my calculator. I'm going to graph e to the x times x to the fourth minus 0.012. And I'm going to look for where that's equal to 0. I might want to tinker with my window here a little bit because it gets really close. So I'm going to take this window, and we know that we can get some pretty small values here for y. Let's go to negative 0.1 to 0.1 and see if we can't see a little bit better what's going on. And I'm going to take my x values a little wider. Let's go from negative 3 to 3. Hopefully I catch this place where it crosses. There we go. All right, now we want the right endpoint, so we want this right-hand intersection point. And so, oh my gosh, oops, chose the wrong command. 0 command, here we go, 0. And we want it to be in between here and here. And we get that x is equal to 0.307. Since we're rounding the interval out, 0.307. And so we are going to say that x is going to be in between 0.307 and negative 0.307. And that is our interval where we can definitely replace e to the x by this with an error no bigger than 0.0005. All right, last one. Example 5 from the 2011 AP Calculus BC free response. Number 6, let f of x equals sine of x squared plus cosine of x. The graph of y equals the absolute value of the fifth derivative of x is shown below. Let p of x be the fourth degree polynomial for f about x equals 0. Using information from the graph shown to the right, show that the difference between the polynomial at 1/4 and the function at 1/4 is less than 1 over 3,000. This is another way for us to express the error. It's the difference between the polynomial and the function. So we're looking for the fourth degree error here. So we want the maximum of the fifth derivative of the function times the maximum of absolute value of x minus a, which we're looking at it, it's centered at 0. We're finding the approximation at 1/4. So this is going to be 1/4 to the fifth. That's the maximum value on that interval, all over 5 factorial. Now looking at this graph, we're looking for the maximum value of this on the interval from 0 to 1/4, which is this interval right here. Now, I can see that the maximum value is one of these two values right here. Those are probably the same value. I can't tell exactly where that is on the graph, but one thing that I know for sure is I know for sure that it's less than 40. So I'm going to put 40 in here. And then I'm going to calculate this value. And this is a non-calculator section, so I'm going to go ahead and calculate this without a calculator. 1 over 1,024. This is 5 factorial, which is 120. So this is going to be 1/3 times 1 over 1,024, which is 1 over 3,072. That's our bound for our error. Our error has to be less than or equal to that. And that is indeed less than 1 over 3,000. And so we're good to go. All right, that concludes our lesson here on the Lagrange Error Bound. Get yourself some practice with these problems, see how you do. And we'll come back next time for section 10, what are we on now? 1013 coming up next? Holy smokes, we're almost there. All right, everybody, have a good rest of your day, and we'll see you next time. Bye-bye for now.